Okay, so now we're going to add the same three vectors mathematically. And I dropped an H there. It says mathematically. How's that? Is that impressive or what? I'm leaving it. So we have the same three vectors. D is A plus B plus C. D is the resultant, so we're adding A and B and C to get D. So graphically, D is the answer. But now what we want to know is how to find out exactly how long D is and exactly what its direction is. So what we're really looking for here, when I ask for D, what this question mark means is I want to know the magnitude of D and I want to know theta, because theta, this angle right here, tells us the direction of D. Pardon me. Okay. So when I'm asking for D, I'm really asking for the magnitude of D, how long this is. That is, how far from where we started are we? Right? We started at the origin. After we take this path here, we end up here, but how far are we actually from the origin? That's what D is. It's the magnitude of the total displacement, the resultant vector. And also I want to know what angle, that is, what direction I am away from the origin. Am I over here? Am I over here? Am I over here? Over here? Where around the origin am I? The angle theta tells us that. I want D and I want theta. I've got these three vectors. A, 3.75 meters north, B, 2.25 meters east, and C, which I had written as 2 meters last time, but should have been written as 3 meters to the southeast. Given that information that I've got here, 3.75 meters north, 2.25 meters east, 3.00 meters southeast, what is D and theta? That is, how long is the resultant vector, the pink one, and at what angle does it sit? Okay. The first step here is you can't just add. Okay, you can't just add 3.75 plus 2.25 plus 3. You do that, you get 9. But this distance D is not 9 meters. It's way less than that, because you kind of loop back on yourself a little bit. So the first thing to do is to find the components of A, B, and C. We have to find the x parts and the y parts for each of these vectors. That's what components means. Think back a couple of videos. So we need to find A sub x, A sub y. We need to find B sub x, B sub y. We need to find C sub x and C sub y. Now remember, A sub x simply means how far the vector A goes in the x direction. AY tells us how far the vector A goes in the y direction. BX tells us how far B goes in the x direction. BY tells us how far B goes in the y direction, and so forth. So how far does A go in the x direction? Just look at A here. It's pointing straight up. Does it, at the end of A and at the beginning of A, you're in the same x value, which is 0. It doesn't point in the x direction at all. This vector A is entirely in the y direction. It's going straight north, which is the y direction. So the x component of A, of the vector A, is 0. Now, how far does the vector A go in the y direction? Well, it goes 3.75 meters. So that is the y component. It happens that this vector lies entirely in the y direction, so it has the same y, the y component is the same as the magnitude of the vector itself, 3.75 meters. Now let's look at the components, the x and y parts of vector B. Bx, how far does it go in the x direction? Well, we know that B is 2.25 meters east, which is in the x direction. So again, B lies entirely along the x-axis. Now, it's not located on the x-axis. It's located up here in this drawing. But it points in the x direction. That's what I'm trying to say. And like I said last video, tried to make clear you can move vectors around. So we could move it down here and put it on the x-axis. right, if we wanted to, and we could see then that it points perfectly in the x direction and not at all in the y direction. So the y component of the B vector is my favorite number, 0. Okay. So those two vectors are easy because each one of them has a component of 0 along x or y. But look at C, y'all. Look at C. C begins and ends at a different value of x and y. Right? A begins and ends at the same value of x. B begins and ends at the same value of y. But C changes in both x and y. The vector C does not lie along either axis, and you can't make it so. If you move this vector around, it's got to stay pointed sort of down and to the right, to the southeast, so it's never going to lie along both. So neither Cx nor Cy is going to be equal to 0. Here we have to go back to our trigonometry, and you'll see that, look, this vector C is very much like the vector that we had in downtown Decatur when we were going positive in the x direction and negative in the y direction. Remember, it pointed to the southeast. We were going from the courthouse to Victory. That's a southeastern direction. So this vector here, C, let's take a look at it. Let's blow it up a little bigger. Here's our vector C. I'm just taking a closer look at it. Obviously this is longer than this, but I'm just zooming in on it. Notice that it, in the same way as the displacement vector in downtown Decatur, it has an x part and a y part. So here is C, here is Cx, and here is Cy. So we have to find both Cx and Cy for this vector because it lies neither along the x nor the y axis. And we can do this using our rules from trigonometry. Cx is going to be the hypotenuse, which is C, right, times the, well, notice here that x is the, here's our angle. We've got to pick an angle, of course. Here's our angle theta. We can pick any angle we want to, but typically it's convenient to pick the angles that come off the positive x direction. But you can pick any angle you want to. It doesn't really matter at all. So C is going to be, Cx is going to be C. Now this is the adjacent in this particular triangle. Adjacent is cosine. So C cosine theta. Cy is going to be C sine of theta. Okay. Now we know what C is equal to. C is equal to 3 meters. Do we know what theta is? Well, this vector here, C, points directly to the southeast. So it's midway between the x-axis, the positive x-axis, and the negative y-axis. The compass point, southeast, is directly between east and south. So this angle theta is going to be 45 degrees. Because my instructions were to walk directly southeast for 3.00 meters. So that angle there has to be 45 degrees. So Cy is equal to 3.00 meters times cosine of, actually it's negative 45 degrees because it's down below the x-axis. And that's gonna, and then Cy is going to be 3.00 meters times sine of negative 45 degrees. Okay. And when you do this, you'll get Cx is, I think it's 2.121 meters, and for Cy you're going to get negative 3. No. You're going to get the same magnitude, negative 2.121 meters. Now before I march on, let me say that this might be a little confusing about this negative 45 and the 45 there. There's two ways of doing this. One is to always measure every angle from the positive x-axis. And if you did that, this would be a negative angle because you're going down from the positive x-axis. Another way to do it is to keep up with these signs here is just to call this 45 degrees, but know that CY is going to be negative because it points down. I know that's a bit of a confusing spot for you, and we'll come back to this in our work sessions. But there's two ways of handling the signs with these vectors. And the way I've handled it here is to say that we always measure angles relative to the positive x-axis. That's this direction on the board, and this is down from that, so it's negative. Again, another way of handling it is to call all angles positive, but just keep track knowing that this is going to be a positive x component, and that's going to be a negative y component. Okay. You can do it either way. So we have all our components now. We know AX, we know AY, BX, BY, CX, and CY. Now the second step, right, the first step was to find the components. Now we have the components. We have 3 X's and 3 Y's. Second step is to add like components. The x component of the resultant is going to be ax plus bx plus cx without the vector signs. Okay, so ax 0 plus bx 2.25 meters plus cx 2.121 meters. So we have dx, the x component of our resultant vector, is 4.371 meters. Okay. We're adding like components. dy is going to be ay plus by plus cy, which is 3.75 meters, plus 0 minus 2.121 meters, which gives us a y component of 1.629 meters. Okay. These are the x and y components of our final pink vector. Okay. What we're looking for is the magnitude of our final pink vector and the angle theta. To do this, we do what we did before. We use the Pythagorean theorem. D squared is dx squared plus dy squared. That's how we find d, the magnitude of the pink vector. That is, how far away did you end up after taking these 3 paths from the origin? That's what d is. And we're low on time with the video here, so I'm just going to give you the answer. It's 4.66 meters. That is the magnitude. So d equals 4.66 meters. That's how far away. If you lay down a meter stick along like a meter stick between the origin and where you ended up, you would be 4.66 meters away from where you started. And theta, that is the angle here between the positive x-axis and d, is the inverse tangent of dy over dx. Again, I don't have time to go through the math, step through the math. I don't have the time, nor do I have the space on the board. That equals what angle here? 20.4 degrees. So this angle here is 20.4 degrees, and that is your answer. You have gone 4.66 meters at an angle 20.4 degrees above the positive x-axis. That's how you add vectors. You have to find, this is the big deal here, you have to find the components first of each of the vectors in the sum. And then you have to add like components. And the x component of your final vector, of your resultant, is the sum of the straight algebraic sum, straight arithmetic sum of the three x components. The y component of your resultant is the straight arithmetic sum of the three y components. The trickiest part here might have been this. Okay, I acknowledge that. You need to understand where that came from, where these numbers came from, here and here. You have plenty of chances to play with this in the homework. You'll be happy to find out. Okay. But that's it for that example. Next up, I'm going to make a few more comments about vectors to wrap up our vector week here. Okay? See you then. We're going to talk about unit vectors and subtracting vectors. Treat both of them quite briefly. But we're going to come back to this example to talk about unit vectors. Okay? Bye.